Tonight, we're going to talk about the fact that every other world in this solar system is dead, and that we know, in detail, exactly how each one of them died. Venus was cooked. It almost certainly had oceans once, possibly for billions of years, and then it lost every drop of them to a sky that would not let heat escape. We can still measure the fingerprint of that water in what is left of its atmosphere. Mars was drained. Its air leaked away into space a few hundred grams at a second until the rivers on its surface had nowhere left to run, and you can still see the dry channels from orbit. Mercury was stripped. Something struck it hard enough to tear most of the planet away, and what is left going around the Sun today is closer to an exposed metal core than a world. Those three are not the failures. Those three are the survivors. They are the ones still substantial enough to have names. And all four of them, including the one you are sitting on, formed from the same cloud of material, at the same time, out of broadly the same ingredients, around the same ordinary star. Four rocky worlds, built in the same place by the same process, handed the same 4.6 billion years to do something with. One of them is currently listening to this. But here's the question almost nobody asks. Not why the other three died, why we didn't. And when you actually go looking for that answer, it is not one thing. It is not simply being the right distance from the Sun. It is not the magnetic field, and it is not the moon, and it is not luck in any sense you could put a number on. It is 7 separate things. 7, each one of them capable of ending this planet, several of which came genuinely close, and every single one of which had to go our way in order for you to be here tonight hearing about any of it. By the end of tonight, you will know all 7. You will know how we found out about each one, and the specific people who went looking, often for something else entirely. And you will understand the part that is hardest to sit with, which is that not one of the 7 is finished. Every one of them is still running right now, tonight, while you listen. We can measure how fast. On the last one, we can even measure roughly how much time is left. Before we begin, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with the first of the 7, because it is the one that sounds least like a threat. It is not a force, and it is not an object. It is an absence. It is distance. And the first thing to understand about it is that you have never once seen it drawn correctly. Every picture of the solar system you have ever looked at, on a page or a poster or a screen, had to compress the distances by a factor of thousands simply to fit them into a frame. That compression is not a small inaccuracy. It is the reason the system looks like a neighborhood instead of what it actually is. So let's undo it. How far apart are the planets actually? Not in miles. Miles are useless here, and that is the first part of the problem. A number like 93 million does not mean anything to a human brain. It sounds like a big number, and your brain files it next to other big numbers, and then it stops thinking about it. So let's convert. Pick a familiar speed. 60 miles per hour. The speed you drive on a highway without thinking about it. Now imagine a road that goes straight up. At 60 miles per hour, it takes you about 166 days to reach the moon. Not hours, not weeks. More than 5 months of continuous driving, never stopping, never slowing down, to reach the nearest object in the sky. The moon is the closest thing to us in the entire universe. It is the only place human beings have ever stood other than Earth, and it is a 5-month drive. Now keep going. At that same 60 miles per hour, the Sun is roughly 177 years away. You would need to have started driving in the 1840s to arrive today. 3 or 4 generations of drivers, handing the wheel to each other, to cross the gap between us and our own star. And the Sun is close. The Sun is our immediate neighbor. Everything else is further. Mars, at its closest approach, is about 63 years of driving. At its furthest, when it sits on the opposite side of the Sun from us, it is over 460 years. That variation matters, and we will come back to it, because it is the reason we can only launch missions to Mars during a narrow window that opens once every 26 months. Miss the window, and you wait more than 2 years for the next one. The universe does not hold the door. Jupiter is roughly 740 years of driving at its closest. Saturn, about 1,400 years. Uranus, around 3,100. Neptune, at 2.8 billion miles, is a drive of more than 5,300 years. To put that in perspective, if a driver had left for Neptune at the moment the first Egyptian pyramids were being built, and had driven at highway speed every hour of every day since, without a single stop, they would still be well short of arriving. And Neptune is not the edge. Neptune is where the planets happen to stop. The solar system keeps going for a very long time after that. This is the first of the 7, and it is the foundation of everything else tonight. Every picture of this system compresses the emptiness. It has to. If you drew the solar system to scale on a page where Earth's orbit was 1 inch across, Neptune's orbit would be 30 inches away, and every planet would be an invisible speck. If you scaled it so that the Sun was the size of a basketball, Earth would be a grain of sand about 90 feet away, and Neptune would be another grain of sand roughly half a mile down the street. Everything in between would be nothing. That word, nothing, is doing a lot of work. Let's be precise about it. The interplanetary medium is not a vacuum in the perfect sense. There are particles out there, but in the space between Earth and Mars, you are looking at something on the order of a handful of atoms per cubic inch. Compare that to the air in the room around you, which contains something like 400 billion molecules in that same volume. The gap is not close. It is not a matter of degree. Interplanetary space is emptier than the best vacuum any laboratory on Earth has ever produced, and it is emptier by an enormous margin. Which brings us to the part that most people never think about, because emptiness does not sound dangerous. Here is why it is. Think about swimming away from a beach. For the first 100 yards, everything is fine. You can see the shore. You can hear people. If something goes wrong, someone gets to you. Now keep swimming. At some point you cross a line where the shore is still visible but no longer reachable, where the distance itself has become the hazard, and nothing about the water has changed at all. The water was never the problem. The problem is that help is now a function of time, and time has become too long. That is what interplanetary distance does. It is not that space is trying to kill you. It is that space removes every option except the ones you brought with you. We have a very concrete demonstration of this. In April of 1970, Apollo 13 suffered an oxygen tank explosion roughly 200,000 miles from Earth. That crew survived. They survived because they were close enough to loop around the moon and come home on a free return trajectory, because the lunar module could function as a lifeboat, and because a very large number of people on the ground had roughly 4 days to solve the problem. 4 days was tight. 4 days was almost not enough. Now move that same accident to a crew halfway to Mars. Radio delay alone is up to 22 minutes each way, so a simple question and answer takes 3/4 of an hour. There is no free return that gets you home in 4 days. There is no loop. Depending on where you are in the transfer orbit, the fastest possible return is measured in months, and in many cases, the only physically available path home is to continue to Mars first. The distance does not attack you, it simply removes the exits, and there is a second consequence of the emptiness, one that is easier to miss. Light takes time. Sunlight reaching your face right now left the surface of the sun about 8 minutes and 20 seconds ago. If the sun were somehow switched off, you would have 8 minutes of ordinary daylight before anything seemed wrong. Not because the light lingers, but because the last of it is still in transit. Push that further out. Light from the sun reaches Jupiter in about 43 minutes, Saturn about 79 minutes, Neptune roughly 4 hours. This is why the outer solar system is dark in a way that is difficult to convey. Standing on Neptune's moon Triton at local noon, the sun would be a brilliant point of light, still far brighter than any star, but delivering about 1/900th of the sunlight that falls on Earth. Full daylight there is roughly as bright as a moonlit night here. And the delay is not an abstraction. It is an operational fact that shapes everything we can do. When the New Horizons spacecraft flew past Pluto in July of 2015, it was more than 3 billion miles from Earth. A signal took about 4 hours and 25 minutes to cross that gap in one direction, 9 hours for a round trip, which meant that during the flyby itself, the most important 22 hours of a mission that had taken 9.5 years to arrive, there was absolutely nothing anyone on Earth could do. No corrections, no adjustments, no intervention of any kind. The team had loaded the instructions weeks earlier and then sat in a room and waited to find out whether their spacecraft had survived, already knowing that whatever had happened hours ago. Alice Bowman, the mission operations manager, described the wait afterward in plain terms. They had one chance. There was no second pass. New Horizons was moving at more than 30,000 miles per hour, and it was never coming back. The signal arrived. The spacecraft had worked, but notice what the distance did. It turned a team of experienced engineers into spectators watching the past. That's the first layer, and it is the gentlest one because emptiness is passive. It does not do anything to you. It simply refuses to help. Now let's fill the emptiness back in, because something else gets left out along with the distance. Almost every object in the solar system. The 8 planets you were shown are not a census, they are a highlight reel. The actual population of the solar system is not 8. Depending on how you count, it is somewhere in the hundreds of millions, and that estimate is conservative. We have catalogued well over 1 million asteroids in the main belt alone, and current models suggest the belt contains somewhere between 1 and 2 million objects larger than about half a mile across, plus many millions more below that. We have identified more than 3,000 comets. We know of roughly 5,000 objects in the Kuiper belt beyond Neptune, and models put the real number of Kuiper belt objects larger than 60 miles across at more than 100,000. And the Oort cloud, the shell of icy bodies wrapped around the entire system at distances up to and possibly beyond 1.6 light-years, is estimated to contain somewhere on the order of 1 trillion objects. We have never directly imaged a single one of them. Everything we know about the Oort cloud is inferred from the behavior of comets that fall out of it. So the honest picture is a system containing a star, 8 substantial planets, a few hundred moons, and then a vast diffuse population of loose bodies numbering in the hundreds of millions or more, all of it in motion, all of it interacting gravitationally with everything else, forever. At which point you might reasonably expect the solar system to be a shooting gallery. It isn't, and the reason why is the strangest fact in this entire first layer. The asteroid belt, which in every film you have ever seen is depicted as a dense field of tumbling rocks that a pilot must weave through at speed, is essentially empty. If you were placed at a random point inside the main belt, the nearest asteroid to you would typically be around 600,000 miles away. That is more than twice the distance from Earth to the Moon. You would not see it. You would not see anything. You would look around and find yourself in what appears to be completely open space, because it is. Every spacecraft we have ever sent through the belt, and there have been more than a dozen, has crossed it without a single meaningful collision. Not because we aimed carefully, because there is almost nothing there to hit. The total combined mass of every object in the main asteroid belt is about 4% of the mass of the Moon. One object, the dwarf planet Ceres, accounts for roughly 1/3 of that on its own. Take out the 4 largest bodies, and what remains is a scattering of debris spread so thinly across a volume so large that the word field is actively misleading. So the belt is safe. The emptiness protects us. Except that this is exactly the kind of reassurance that falls apart the moment you look at it over a long enough period of time. Low probability multiplied by 4.6 billion years is not low probability anymore. It is certainty with a schedule. And we have the scars to prove it, on the Moon, on Mercury, on Mars, and buried under a layer of clay in the Yucatan Peninsula. We will come back to that. It is the 5th layer, and it deserves the room. For now, Hold on to the shape of what we've established. The solar system is vastly larger than any picture of it implies. The volume is almost entirely empty. That emptiness makes collisions rare, and it also makes rescue impossible. The distance is simultaneously the thing that protects us and the thing that would strand us. One more thing about scale before we move on, because I said Neptune is not the edge, and I want to show you where the edge actually is. In August of 2012, the Voyager 1 spacecraft crossed a boundary called the heliopause. That is the surface where the outward pressure of the solar wind finally drops to match the pressure of the interstellar medium beyond, and the Sun stops being the dominant influence on the surrounding plasma. By one common definition, that is where the solar system ends. Voyager 1 crossed it at a distance of about 11 billion miles. It had been flying for 35 years to get there. But by a different and equally valid definition, the solar system extends vastly further because the Sun's gravity keeps its grip long after the solar wind has given up. The Oort cloud, that shell of icy bodies we mentioned a moment ago, is thought to reach out to somewhere between 1 and 1.6 light years. Convert that back into a highway. At 60 miles per hour, the heliopause is a drive of about 21,000 years. The outer Oort cloud is a drive of roughly 18 million years. And the nearest star, Proxima Centauri, is 4.2 light years away, which at highway speed is a journey of about 47 million years. Which means that if you accept the larger definition, the outer edge of our solar system is a meaningful fraction of the way to the next star. The Oort cloud of our system may actually overlap with the Oort cloud of theirs. There is no wall. There is no line where our system stops and interstellar space begins. There is only a gradual handing over of authority, spread across trillions of miles, from one star's gravity to another's. That is the first of the 7. Distance. And notice what it actually did to us, because it is not what you would expect. It did not threaten this planet. It isolated it. Every one of the 6 things still to come had to reach us across a gap so large that most of them simply never arrive. Hold that thought, because by the end of tonight you are going to realize that the emptiness is the closest thing we have to a defense. But scale on its own is only geometry. It only becomes frightening when you ask what is actually waiting at the far end of any of those drives. Because the diagram gave you 8 planets with clean labels, and it did not tell you what those places are like. So let's go and look. On March 1st, 1982, a Soviet lander called Venera 13 touched down on the surface of Venus. It had been engineered to survive for 32 minutes. It lasted 127. In those 2 hours, it returned the first color photographs ever taken from the surface of another planet. The images show a flat orange landscape of broken slabs of rock stretching to a close horizon, under a sky the color of dull brass. There is a piece of the lander's own lens cap lying in the dirt in one frame. The light is diffuse and shadowless because the sunlight has been scattered so thoroughly by the atmosphere above that nothing on the surface casts a hard shadow at all. Then the spacecraft stopped. It did not run out of power, and it was not switched off. It was cooked and crushed. Venus is the second of the 7. And Venus is where this stops being an abstraction. In every picture you have seen, Venus is a smooth cream-colored circle sitting one slot inward from Earth. It is almost exactly Earth's size. It has 90% of Earth's gravity. It formed from the same disk of material at the same time out of broadly the same ingredients. By every measure available at a distance, Venus is our twin. The surface temperature is about 867 degrees Fahrenheit. That is hot enough to melt lead, and it is hotter than the inside of a self-cleaning oven at its maximum setting. It is also hotter than Mercury, which orbits at less than half the distance from the Sun, and that single fact should stop you for a moment. The planet further from the fire is the hotter one. The atmospheric pressure at the surface is about 92 times what you're experiencing right now. That is the pressure you would find roughly 3,000 feet beneath the ocean on Earth. A human being standing on Venus would not have time to suffocate because the crushing and the cooking would both arrive first, and the atmosphere itself is mostly carbon dioxide with clouds of sulfuric acid suspended above. But here is the part that matters, and it is not the numbers. Venus did not start this way. The current best modeling suggests Venus may have had liquid water on its surface, possibly oceans, possibly for as long as 2 or 3 billion years. Then it crossed a line. The sun brightened slightly. More water evaporated. Water vapor is itself a powerful greenhouse gas, so the atmosphere trapped more heat, which evaporated more water, which trapped more heat. The loop closed on itself and ran away. Eventually, the oceans were entirely in the atmosphere. Ultraviolet light broke the water molecules apart high above the surface, and the hydrogen escaped to space. That hydrogen is not coming back. The water is gone permanently. We can actually see the fingerprint of that. The ratio of deuterium to ordinary hydrogen in the Venusian atmosphere is more than 100 times the ratio on Earth. Deuterium is heavier, so it escapes more slowly, and what is left behind is enriched in it. That enrichment is a receipt. It tells us an ocean's worth of water left the planet. So Venus is not a different kind of world that was always hostile. Venus is a world that ran the same basic process Earth is running, and lost. Hold that thought. It comes back in the final layer, and it is the reason the final layer is the one that unsettles me most. Now move inward. Mercury has almost no atmosphere at all, which means it has no way to move heat around. The side facing the sun reaches roughly 800 degrees Fahrenheit. The side facing away drops to about 290 degrees below zero. That is a swing of nearly 1,100 degrees across a single body, and because there is no air, the transition at the day and night boundary is abrupt. There is no dawn warming. There is a line, and on one side of it the rock is hot enough to soften solder, and on the other side it is colder than anywhere on Earth has ever been. Mercury also has a strange internal structure. Its iron core makes up roughly 85% of the planet's radius, which is wildly out of proportion for a body of its size. Earth's core, by comparison, is about 55% of our radius. The leading explanation is that early Mercury was substantially larger and was struck by something big enough to strip most of its rocky mantle away and fling it into space. What orbits the Sun today may be the exposed metal heart of a planet that was largely destroyed. That is not a metaphor. That is the mainstream model. Now go outward, past Earth, to Mars, because Mars is the one people believe is survivable. The atmospheric pressure on the Martian surface averages about 0.6% of Earth's. That number is worth converting because it is below a threshold that has a name. The Armstrong limit is the altitude at which ambient pressure drops low enough that water boils at normal human body temperature. On Mars, you are well past it. Exposed to the Martian atmosphere without a suit, the saliva on your tongue and the moisture in your lungs and eyes would begin to boil. Not because it is hot, because there is nothing pressing down. The average temperature is around 80 degrees below 0 Fahrenheit. On a good day at the equator in summer, the surface can reach the mid-60s. That sounds pleasant until you learn that the air a few feet above that surface is still far below freezing, because there is not enough atmosphere to hold the heat. And then there is the dust. Martian dust is extremely fine, roughly the consistency of cigarette smoke particles, and it is chemically reactive. The soil contains perchlorates at concentrations of around 0.5% by weight, which are toxic to the human thyroid. The dust is also electrostatically charged and gets into everything. Every Mars rover has degraded in part because of dust. The Opportunity rover, which was designed for a 90-day mission and lasted more than 14 years, was ultimately killed by a global dust storm in 2018 that blocked enough sunlight to drain its batteries. Its final transmission has been widely paraphrased as a report that its power was low and it was getting dark. Mars is the friendliest surface in the solar system after Earth. That is what the friendliest one looks like. Now consider that we have not yet reached anywhere genuinely extreme. Everything so far has been rock, and rock at least gives you somewhere to stand. On December 7th, 1995, a small probe released from the Galileo spacecraft hit the top of Jupiter's atmosphere at 106,000 miles per hour. That is the fastest atmospheric entry in the history of spaceflight, roughly 4 times faster than a capsule returning from the Moon. Its heat shield reached temperatures of about 28,000 degrees Fahrenheit, hotter than the surface of the Sun, and burned away more than 150 pounds of material in a few minutes. Then the parachute deployed and the probe began to fall. It transmitted for 58 minutes. In that time, it descended roughly 100 miles into the atmosphere. It measured winds of about 450 miles per hour, and the important finding was that those winds did not weaken with depth. On Earth, weather is driven by sunlight heating the surface, so it lives in a thin layer near the top. On Jupiter, the winds got stronger as the probe went down, which told us the circulation is driven from the inside by the planet's own internal heat and extends to depths we still cannot map. The probe stopped transmitting at a pressure of about 22 times Earth's sea level, where the temperature was around 305 degrees Fahrenheit. It was not crushed at that moment. It was still falling. Its transmitter simply cooked. What happened afterward is worth sitting with, because it is what the word deep actually means on a gas giant. The probe continued down. Pressure kept rising. Somewhere below, the aluminum structure would have softened and then melted. Below that, the titanium. There is no surface to land on. There is no floor. The atmosphere simply becomes denser and hotter and more compressed, until at some depth the hydrogen itself stops behaving like a gas and begins to behave like a liquid metal, conducting electricity, with no clean boundary anywhere along the way. The probe did not land on Jupiter, and it did not crash into Jupiter. It dissolved into it, and Jupiter's moons are not a refuge. Io, the innermost of the 4 large Galilean moons, is the most volcanically active body in the solar system. It has more than 400 active volcanoes. Some of its eruption plumes rise 250 miles above the surface, high enough that material escapes the Moon entirely and forms a torus of sulfur and oxygen ions wrapped around Jupiter along Io's orbit. The surface is repaved so frequently by volcanic deposits that Io has essentially no impact craters, which is remarkable for a body that has been sitting in the solar system for 4.5 billion years. Every crater has been buried. The cause is not internal radioactivity. It is Jupiter. Io is squeezed by tidal forces from the planet and pulled at by the neighbouring moons Europa and Ganymede, and because those 3 moons are locked in a precise 4:2:1 orbital rhythm, the tugging never averages out. It reinforces, the same way a child on a swing goes higher when the pushes arrive in time with the motion rather than at random. Io's solid surface rises and falls by up to 330 feet on each orbit. The friction from that flexing melts the interior. Io is being kneaded, continuously, forever, by geometry. Europa, next one out, looks calmer. Its surface is a shell of water ice crossed by long reddish-brown fractures, and beneath that shell there is very likely a global ocean containing more liquid water than every ocean on Earth combined. It is one of the best candidates for life beyond Earth that we know of. It is also one of the most lethal surfaces we have ever measured, and we will get to exactly why in the next layer, because the reason has nothing to do with anything you could see, feel, or photograph. Keep going out. On January 14, 2005, the Huygens probe parachuted through the atmosphere of Saturn's moon Titan and returned images of a landscape that is genuinely difficult to categorize. There are river channels, there are drainage networks, there are rounded pebbles at the landing site, smoothed by flowing liquid, sitting on a damp surface. There are lakes and seas near the poles, hundreds of miles across, with shorelines and islands and what appear to be tidal patterns. None of it is water. The temperature on Titan is about 290 degrees below 0 Fahrenheit, at which water ice is as hard as granite and behaves like bedrock. The liquid is methane and ethane. It rains methane on Titan, slowly, in large drops that fall gently through the thick cold air, and the methane collects into rivers, and the rivers run into seas. Titan has a complete weather system, a hydrological cycle, and surface liquid. It is the only other place in the solar system where you could stand beside a shoreline and watch waves. The surface pressure is about 1.5 times Earth's, which is roughly what you would feel 15 feet underwater, so you would not need a pressure suit at all. You would need a heated one, and you would need air. And here is the detail that makes Titan the strangest place on this list. The atmosphere is thick, and the gravity is low, about 14% of Earth's. Run the numbers on that combination, and it turns out a human being with a pair of wings strapped to their arms could actually fly on Titan by flapping. Not glide, fly, under their own muscle power, the way a bird does. A world where you could fly on a beach beside a methane sea at 290 below. Now go all the way out. We have visited Uranus and Neptune exactly once each, both times by the same spacecraft, in a flyby lasting a matter of hours. Voyager 2 passed Uranus in January of 1986 and Neptune in August of 1989. Everything we know about the surfaces and atmospheres of the two outermost planets comes from those two encounters, plus telescope observations since. Neither planet has ever had an orbiter. What Voyager 2 found is genuinely difficult to explain. Uranus is tilted 98 degrees. It is not leaning. It is lying on its side and rolling around its orbit, which means each pole spends 42 years in continuous sunlight followed by 42 years in continuous darkness. The standard explanation is one or more enormous impacts early in its history, and the honest position is that we do not have a fully satisfying account of how a planet that size gets knocked over. Neptune, further out and receiving about 40% less sunlight than Uranus, is the more active of the two by a wide margin. It radiates roughly 2.6 times more energy than it receives from the Sun, meaning it has a substantial internal heat source we have not identified, and it has the fastest winds ever measured anywhere in the solar system. Voyager 2 clocked them at about 1,200 miles per hour. Sit with that comparison for a second. The strongest sustained winds ever recorded on Earth are in the region of 250 miles per hour, in a tornado for a few seconds across a few hundred yards. Neptune's winds are nearly 5 times faster. They are continuous, and they wrap an entire planet 4 times Earth's diameter, on a world that receives about 1,900th of our sunlight, which is to say almost none of the energy that drives weather here. Deep inside both planets, the pressure and temperature conditions are thought to break apart the methane in their interiors, freeing carbon that crystallizes into diamond. Laboratory experiments using high-powered lasers to reproduce those conditions have produced exactly that result. So the current best understanding is that it rains diamonds inside Uranus and Neptune, continuously, and that the diamonds slowly sink toward the core. And Neptune's largest moon, Triton, orbits backward. Every other large moon in the solar system orbits in the same direction its planet rotates, because that is what you get when a moon forms in place from a disk. Triton goes the other way, which is the signature of a captured object. It was almost certainly a Kuiper belt body that wandered too close and was caught, which means it is not permanent. Triton is spiraling inward. In somewhere between 1 and 4 billion years it will cross the Roche limit, the distance at which tidal forces exceed a body's own gravity, and it will be torn apart. Neptune will get a ring system out of it. That is the second of the 7. And the honest summary of it is short. There is no second Earth. There is not a single location among the hundreds of solid surfaces in this solar system where an unprotected human being would survive for more than a few seconds, and in most cases the correct number is measured in fractions of a second. The range of environments runs from lead melting to granite-hard ice, from pressures that would crush a submarine to pressures so low your blood would boil. You might think that is the worst of it. The hostile surfaces, the crushing pressures, the temperature extremes. That is what people mean when they say space is dangerous. But that answer is incomplete, and in an important way, it is the wrong worry entirely. Because everything in this layer is something you could see coming. You can photograph a volcano. You can measure a pressure. You can build for a temperature. The next layer cannot be seen at all, It has no color, no sound, no sensation. It passes through the walls of a spacecraft and through the walls of your body without you knowing. And by the time you have any evidence that it happened, the damage is weeks old. So what is actually filling all that empty space we spent the first layer establishing? Between the 4th and the 7th of August 1972, the Sun produced one of the most intense particle storms of the entire space age. The timing is what makes it worth telling. Apollo 16 had returned from the Moon in April of that year. Apollo 17 would launch in December. The storm arrived in the gap between them, in a 4-day window when no human being was outside Earth's magnetic field. Later analysis of what that storm would have delivered to a crew on the lunar surface, or worse, to a crew in transit with only the thin aluminum of a command module between them and open space, produced estimates in the range of several hundred rem absorbed over a matter of hours. At the upper end of those estimates, that is acute radiation sickness, vomiting within hours, collapse of the immune system over the following days, a serious probability of death before the return trajectory brought them home, and no possible intervention from the ground. The astronauts of Apollo 16 and Apollo 17 have both spoken about this in later years. The gap was not planning. Nobody could have planned it. There was no forecasting capability in 1972 that could have predicted that event with any useful lead time. The gap was luck. This is the third of the 7. It is the first one you cannot see, and it is the one that most seriously constrains what our species can actually do out there. Let's define the thing properly, because the word radiation gets used loosely, and the looseness hides what is dangerous about it. There are 2 separate populations of particles moving through the solar system, and they behave in almost opposite ways. The first comes from the Sun. The Sun is continuously boiling off its outer atmosphere in a stream of protons and electrons called the solar wind, moving at roughly 1 million empire, and periodically it releases much larger and much faster bursts. These are solar particle events, and they are the reason the 1972 storm was survivable in principle. Solar particles are relatively low energy. A few inches of the right material will stop most of them. If you can get behind mass quickly, you are largely fine. The second population is far worse, and there is no known way to stop it. Galactic cosmic rays are atomic nuclei that have been accelerated by supernova shock waves somewhere else in the galaxy, sometimes millions of years ago, and have been traveling ever since. They arrive from every direction at once. They arrive at a substantial fraction of the speed of light, and crucially, some of them are not protons but heavy nuclei, iron and other elements, carrying enormous energy in a single package. Here is why that matters, and here is the analogy that finally made it clear to me. Think about the difference between being hit by a stream of sand and being hit by a single bullet carrying the same total energy. The sand spreads its energy across a wide area and does little damage anywhere. The bullet concentrates all of it into one narrow track. A heavy cosmic ray nucleus passing through your body does not deposit its energy diffusely. It punches a track straight through, and everything along that track, every cell, every strand of DNA, absorbs a concentrated dose. Cells can repair scattered damage reasonably well. Cells are much worse at repairing a clean cut through both strands at once. Now the part that genuinely surprises people the first time they hear it. Shielding can make galactic cosmic rays worse. When one of these high-energy nuclei strikes a thin layer of material, it does not stop. It shatters, and the fragments spray outward as a shower of secondary particles, including neutrons, which are themselves biologically damaging and notoriously hard to block. Add a modest amount of aluminum to a spacecraft hull, and in some energy ranges you increase the dose inside rather than decrease it. You have not built a shield. You have built a target that sprays. To actually reduce galactic cosmic ray exposure, you need a great deal of mass, on the order of several feet of water or rock, or you need hydrogen-rich materials like polyethylene, which shatter the incoming nuclei into less harmful fragments. Both solutions weigh an enormous amount, and weight is the single most expensive thing in spaceflight. So what is the actual number? We have a good measurement, and we got it in a clever way. When the Curiosity rover flew to Mars between November of 2011 and August of 2012, it carried an instrument called the Radiation Assessment Detector, and it left that instrument switched on during the cruise, sitting inside the sealed capsule in roughly the position a human crew would occupy. So we did not have to model the transit dose. We measured it. The result was about 0.66 sieverts for a round trip, from the cruise phase alone, before adding any time spent on the Martian surface. For context, the lifetime limit NASA has historically applied to its astronauts corresponds to roughly a 3% increase in fatal cancer risk. The measured round-trip dose puts a crew at or beyond a substantial fraction of a career limit on a single mission, and that assumes the sun stays quiet the entire time. This is not a problem we have solved. It is a problem we currently manage by going fast, going rarely, and accepting the risk. Now take that and go to Jupiter. Jupiter has a magnetic field roughly 20,000 times stronger than Earth's. That field captures charged particles and accelerates them, and the volcanoes of Io feed about a ton of fresh sulfur and oxygen ions into the system every second. The result is a radiation environment that has no equal anywhere in the solar system. At the orbit of Io, the dose rate is on the order of 3,600 rem per day. On the surface of Europa, further out and therefore gentler, it is around 540 rem per day. Those numbers need converting, because rem is not a unit anyone has intuition for. A dose of roughly 500 rem delivered over a short period is generally considered lethal to about half of the people who receive it, without medical intervention. So an unprotected human being, standing on the surface of Europa, in a suit that handled the vacuum and the cold and everything else perfectly, would absorb a likely fatal dose in approximately 1 day. Not from the vacuum, not from the temperature, which is around 260 degrees below zero, from standing in a place where the sky itself is delivering energy into their body at a rate their cells cannot keep up with. Europa may well have a global ocean with more water than Earth. It may be the most promising place to look for life we have, and its surface is a place where a human would receive a fatal dose faster than they could get a message home and back. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, absorbed more than 4 times the total radiation dose it had been designed to withstand. It suffered repeated computer resets, memory errors, and instrument faults throughout the mission. Engineers spent years nursing it through failures that were, in the most literal sense, caused by the environment slowly disassembling its electronics one particle at a time. The Juno spacecraft, which arrived at Jupiter in 2016, carries its most sensitive components inside a titanium vault with walls roughly 1/3 of an inch thick, weighing around 400 pounds. That vault does not eliminate the problem, it slows it down. Now let's come back to Earth and ask the obvious question. If all of that is out there, why are you fine? 2 reasons, and they are the only 2. The first is the magnetic field. Earth generates a magnetic field from the motion of liquid iron in its outer core, and that field extends tens of thousands of miles into space, deflecting the solar wind around the planet the way a rock in a stream diverts the water around it rather than stopping it. Charged particles that do get captured are held in the Van Allen belts, donut-shaped regions of trapped radiation, well above your head. The second is the atmosphere. The column of air above you is equivalent, in shielding terms, to about 13 feet of concrete. That is more mass than any spacecraft we could plausibly launch. You are living at the bottom of a shield we could never afford to build. Take either one away and the situation changes fast, and we have a worked example. Mars has essentially no global magnetic field today, though the magnetized rocks in its ancient southern crust tell us it had one in its first few 100 million years. When that dynamo shut down, the solar wind gained direct access to the upper atmosphere. The MAVEN spacecraft, which arrived in 2014 specifically to measure this, watched it happening in real time and found that Mars is currently losing atmosphere to space at an average rate of a few hundred grams every second, rising sharply during solar storms. A few hundred grams per second sounds trivial. Multiply it by 4 billion years. That is how you strip a planet. Mars did not lose its atmosphere in a catastrophe. Mars lost its atmosphere the way a slow leak empties a tire, over a length of time that makes the rate irrelevant. The rivers dried up because the pressure fell below the point where liquid water could exist on the surface, and the pressure fell because there was nothing holding the air down against a star that never stopped blowing. That is the shape of this entire layer. Nothing dramatic happens. There is no explosion, and no impact and no moment. There is a steady invisible flux, and it either accumulates in your cells or it accumulates in your planet's history, and either way you do not notice until the total has already been reached. There is one more thing about this layer, and it is the detail that made it real for me, because it is the only part of the radiation environment that a human being can actually perceive. During Apollo 11, on the way to the moon, Buzz Aldrin mentioned something odd. With his eyes closed in the darkened cabin, he was seeing occasional flashes of light. Not a glow, discrete points and streaks, appearing and vanishing. He was not the only one. When the crews were systematically asked about it afterward, nearly every Apollo astronaut reported the same thing. On later missions, they ran deliberate experiments, sitting in darkness with eyes covered for an hour at a time, counting flashes and recording their apparent shapes and directions. The explanation is that a cosmic ray nucleus is passing directly through the eyeball and triggering the retina, or in some cases passing through the visual cortex itself. The astronaut is not seeing light. There is no light. A single charged particle is depositing energy along a track through neural tissue, and the brain interprets the signal the only way it knows how. Astronauts on the International Space Station report the same phenomenon today, and the rate goes up sharply in one particular region of the orbit. That region is called the South Atlantic Anomaly. Earth's magnetic field is not perfectly centered on the planet and not perfectly symmetrical, and over a broad area off the coast of Brazil, the inner Van Allen belt dips much closer to the surface than it does elsewhere. Spacecraft passing through it experience a sharp rise in particle flux. Satellites routinely power down sensitive instruments while crossing it. The Hubble Space Telescope does not take observations while it is inside the anomaly, because the data would be corrupted. The station passes through it several times a day. I find that detail more affecting than any of the dose numbers, and I think the reason is this. Every other hazard tonight has been something you would experience as an event. This one you experience as a flicker behind closed eyes, on an ordinary evening, in a well-lit spacecraft, while trying to sleep. There is no sensation of damage. There is only a small silent point of light that was never there, and the knowledge of what had to happen to produce it. That is the third of the 7. And notice how it changed the character of the problem. The first 2 were about places. Distance is a fact about geometry, and hostile surfaces are facts about specific locations. You can route around a place. Radiation is not a place. It is a condition of the volume. It is present everywhere in the solar system, all the time, and the only genuine protection is to put a great deal of matter between yourself and the sky. But so far I have been describing the sun as though it were a steady source, a constant lamp, humming along, throwing out a predictable wind. It is not. And that assumption, which sits quietly underneath almost everything we have built on this planet in the last 150 years, is the 4th layer. On the morning of September 1st, 1859, an English astronomer named Richard Carrington was doing what he did most clear mornings. He had a private observatory at his home in Red Hill, and he was projecting an image of the sun onto a screen through his telescope, tracing the outlines of sunspots by hand onto paper. It was routine work. He had been building a catalogue for years. At around 11:18 in the morning, 2 points of intensely bright white light appeared within a large sunspot group he was drawing. They were so bright that Carrington initially assumed something had gone wrong with his equipment, that a hole had opened in the cloud cover and direct sunlight was leaking onto the screen. He ran to fetch someone else to confirm what he was seeing. By the time he got back, Roughly a minute later, the points had already faded. The whole event lasted about 5 minutes. 17 hours later, the Earth's magnetic field convulsed. Auroras appeared over Cuba, over Hawaii, over Colombia, thousands of miles from the poles where they belong. In the northeastern United States, the light was reported as bright enough to read a newspaper by at 1 o'clock in the morning. Gold miners in the Rocky Mountains reportedly got up and started making breakfast, having concluded from the sky that it was dawn. And the telegraph network, which in 1859 was the only long-distance communication technology on Earth, stopped behaving like a machine. Operators reported sparks jumping from their equipment. Some received electric shocks. Telegraph paper caught fire in at least a few offices. And then something genuinely strange happened. Operators in Boston and Portland discovered they could disconnect their batteries entirely and continue sending messages to each other, powered by nothing but the current the sky was inducing in the wire. That is the Carrington event, and it is the most intense geomagnetic storm in recorded history. Carrington himself, to his credit, was careful. He noted the coincidence between what he had seen on the Sun and what happened to Earth the following day, and he explicitly declined to claim causation from a single instance. The connection between solar activity and terrestrial magnetic storms would not be firmly established for decades. This is the fourth of the 7. The Sun is not a lamp. It is a variable magnetic object with a temper, and you have spent your whole life picturing it as a smooth yellow disk, because a smooth yellow disk is exactly what it looks like from 93 million miles away, through an atmosphere that filters out everything interesting. Start with what it actually is. The Sun contains about 99.86% of all the mass in the solar system. Every planet, every moon, every asteroid and comet and grain of dust, all of it combined, is a rounding error on the Sun. Jupiter, which is more massive than all the other planets put together, accounts for most of what is left. At the core, the temperature is about 27 million degrees Fahrenheit, and the pressure is roughly 250 billion times Earth's atmospheric pressure. Under those conditions, hydrogen nuclei fuse into helium, converting about 4 million tons of matter directly into energy every second. The Sun has been doing this for 4.6 billion years and has burned through only a fraction of its available fuel. Here is a fact about that energy that I find genuinely striking, and it changes what you are feeling when you stand in sunlight. A photon produced by fusion in the core does not fly straight out. The interior is so dense that it travels a tiny distance, collides with a particle, gets absorbed, gets re-emitted in a random direction and repeats. It stumbles. Estimates for how long it takes a unit of energy to work its way from the core to the surface range from about 10,000 years to over 100,000 years, depending on the model. Then, once it reaches the surface, it crosses the 93 million miles to your face in 8 minutes and 20 seconds. The last leg of the journey is the fastest part by an overwhelming margin. The sunlight warming your skin spent tens of thousands of years getting out of the building and 8 minutes getting to you. Now, the temper. The Sun's interior does not rotate as a solid body. The equator completes a rotation in about 25 days, while the polar regions take closer to 35. That differential rotation drags the Sun's internal magnetic field around, winding it up like a rubber band being twisted, tighter and tighter, over a period of years. Eventually, the wound-up field becomes buoyant, and loops of it break through the surface. Where those loops emerge, they inhibit the convection that brings heat up from below. That patch of surface cools by a couple of thousand degrees relative to its surroundings. It is still glowing at around 7,000 degrees Fahrenheit, still blindingly bright in absolute terms, but against the rest of the photosphere it looks dark. That is a sunspot. A sunspot is not a hole, and it is not cold. It is a place where the magnetic field is strong enough to interfere with the flow of heat. The number of sunspots rises and falls on a cycle, averaging about 11 years, and it has been counted continuously since the 1700s, which gives us one of the longest-running data sets in all of science. At solar maximum, the disk can carry 100 or more spots. At minimum, it can go weeks with none at all. And when those twisted magnetic field lines snap and reconnect into a simpler configuration, the energy stored in the twisting gets released all at once. There are two distinct products of that release, and confusing them is the most common mistake people make about space weather. A solar flare is a burst of electromagnetic radiation. X-rays, ultraviolet, sometimes visible light, which is what Carrington saw. Because it is light, it travels at light speed, so it arrives 8 minutes and 20 seconds after it happens. There is no warning. The first evidence you have that a flare occurred is the flare arriving. Flares ionize Earth's upper atmosphere and can black out shortwave radio on the sunlit side of the planet within seconds. A coronal mass ejection is different. It is matter. A CME can hurl 1 billion tons of magnetized plasma off the Sun at speeds ranging from around 600,000 miles per hour to, in extreme cases, more than 6 million mph. Because it is matter and not light, it takes time to cross the gap, typically 1 to 3 days, occasionally, for the fastest events, as little as 15 to 18 hours. The Carrington CME made the crossing in about 17 hours, which is roughly 4 times faster than average, and the reason it managed that is thought to be that an earlier ejection had already cleared a path through the solar wind ahead of it. So the flare is the warning shot, the CME is the thing that matters, and when a CME's magnetic field is oriented opposite to Earth's, the two fields connect, and enormous amounts of energy pour into our magnetosphere. What that does to a planet with no electrical infrastructure is a light show. What it does to a planet with several million miles of conducting wires strung across its surface is a different matter entirely. A geomagnetic storm causes the magnetic field at ground level to fluctuate. A changing magnetic field induces current in any long conductor sitting inside it. This is not exotic physics. It is the same principle that runs every electrical generator on Earth. The difference is that the conductors in question are national power grids, and the induced currents are direct current flowing into equipment designed for alternating current. The vulnerable component is the transformer. Large grid transformers push alternating current through an iron core, and a slow-moving induced direct current saturates that core, so the transformer starts drawing enormous reactive power and heating up in ways it was never built to handle. Insulation degrades. In severe cases, the unit is destroyed. We have watched this happen. On March 13, 1989, a geomagnetic storm hit the Hydro-Quebec grid. The system went from normal operation to complete collapse in 92 seconds. 6 million people lost power in the middle of a Canadian winter. It took about 9 hours to restore. On the same night, a large transformer at the Salem nuclear plant in New Jersey was damaged badly enough to require replacement. The 1989 storm was roughly a third as strong as the Carrington event. Stop for a second and picture what that actually means where you are sitting. Not the grid as an abstraction, the specific building you are in. Water arrives at your tap because a pump is running somewhere. Food arrives at the shop nearest you because a refrigerated chain of trucks and warehouses never stops. The money in your account is a number in a building that needs power to remember it. Your heating, your phone, the tower your phone talks to, the hospital nearest you, and the pumps at the filling station you would drive to if you decided to leave, are all downstream of the same handful of machines. 9 hours in Quebec was an inconvenience that people still talk about. The reason the number was 9 hours and not 9 months is that the transformers mostly survived. Now, here is where I have to be careful, because this topic attracts a great deal of exaggeration, and the honest version is unsettling enough without it. We do not know precisely what a Carrington-class event would do to a modern grid. The estimates vary widely, and they vary because the answer depends on details nobody can fully model. It depends on the storm's magnetic orientation, on the season, on the time of day, on ground conductivity beneath specific substations, on how much warning operators get and what they do with it. Serious published estimates for economic damage in the United States alone have ranged from hundreds of billions of dollars up into the trillions, and the wide range is itself the finding. What is not in dispute is the recovery problem. The largest grid transformers are not stock items. They are custom built, they weigh hundreds of tons, they are typically manufactured to order with lead times measured in many months, and moving one requires specialized rail transport. Losing a handful is a manageable inconvenience. Losing a large number simultaneously, across multiple countries, when the factories that build them are themselves without power, is a different category of problem. And the honest answer about frequency is that we do not have good statistics, because we have only been watching carefully for about 60 years, and events this large are rare. Published estimates for the probability of a Carrington-class storm striking Earth in a given decade have ranged from under 1% to around 12%, and the disagreement between those figures reflects genuine uncertainty in the underlying data rather than carelessness. But we do have one piece of evidence that should be more widely known. In July of 2012, the Sun released a CME of Carrington-class intensity, possibly stronger. It was measured directly by the Stereo spacecraft, which happened to be sitting in the path, and the measurements are unambiguous. It missed Earth. It missed because it erupted from a part of the Sun that was not facing us at the time. Earth had passed through that region of its orbit about a week earlier. Had the eruption occurred 9 days sooner, it would have hit us squarely, and we would have found out empirically what the answer is. Daniel Baker, a space physicist at the University of Colorado who studied the event, summarized it afterward in about the plainest language available. If it had happened a week earlier, Earth would have been in the line of fire. That is the fourth of the 7, and I want to be precise about why it belongs on the list. Nothing about the Sun's behavior in 2012 was unusual for the Sun. It was an ordinary event for a middle-aged star with a magnetic cycle. The Sun has been doing this the entire time our species has existed. What changed is us. Somewhere in the last 150 years, we wrapped the planet in a conducting web and then built everything else on top of it, and in doing so we became sensitive to a category of event that had previously been a curiosity worth writing down in an observing notebook. The danger did not increase, our exposure did. And the deeper problem is the one Carrington ran into in his study, projecting the Sun onto a screen with a pencil in his hand. We can see a flare 8 minutes after it happens, which is to say, after it has already reached us. We can track a CME once it is in transit and give perhaps a day of warning, and even then our predictions of its magnetic orientation, the single factor that most determines whether it does damage, remain poor until it is roughly 30 minutes out. 30 minutes is not enough time to shut down a continent's grid in an orderly way. We are not blind. We are just very nearly too slow. And there is a longer version of the Sun's variability that gets less attention than the storms, because it operates over centuries rather than days. Between roughly 1645 and 1715, sunspots very nearly disappeared. Astronomers across Europe were watching carefully by then, with telescopes keeping records. Over a span of about 30 years within that period, fewer than 50 sunspots were observed in total. A typical 30-year span today would produce something in the region of 40,000 to 50,000. That interval is called the Maunder minimum, after Edward Maunder and his wife Annie Maunder, who worked through the historical observing records in the 1890s and established that the absence was real rather than a gap in the data. It coincides with the coldest stretch of what is often called the Little Ice Age in Europe. The Thames froze hard enough to hold markets on the ice. Alpine glaciers advanced far enough to destroy villages. Now, the honest version, because this connection gets badly overstated. The temperature drop associated with reduced solar output during the Maunder minimum is generally estimated at a few tenths of a degree globally, which is real but modest, and a substantial part of the cooling in that period is attributed to volcanic activity. Solar variability of this kind is not a large enough lever to explain the whole climate record, but it establishes something that matters for tonight. The 11-year cycle is not the whole story. The Sun has modes. It can go quiet for decades at a time, and it can also run unusually active, and we cannot currently predict which it will do next. That is the part that should be said plainly. Solar cycle prediction remains genuinely difficult. Forecasts for the current cycle issued before it began differed substantially from one another, and the observed activity has run above the consensus prediction. We are getting better at it. We are not good at it. So the star at the center is variable, and the volume around it is filled with particles we cannot block. That accounts for the energy. But there is still the matter of the physical objects, the hundreds of millions of loose bodies we counted in the first of the 7, the ones no picture of this system has ever had room for. I told you the belt was almost entirely empty, and that is true. And it is exactly the kind of true statement that lulls you, because empty is a statement about a moment, and the solar system does not deal in moments. At 9:20 in the morning on February 15th, 2013, people across the Chelyabinsk region of Russia looked up because the sky had gotten brighter than the sun. An object roughly 66 feet across, weighing about 13,000 tons, entered the atmosphere at approximately 42,000 miles per hour. It came in at a shallow angle and travelled for about 30 seconds, leaving a brilliant trail visible for hundreds of miles, before the aerodynamic stress tore it apart at an altitude of roughly 14 miles. The airburst released energy equivalent to about 500 kilotons of TNT, somewhere in the region of 30 times the Hiroshima bomb, though spread across a wide area and released high in the atmosphere rather than at the surface. Because the light arrived before the sound, there was a delay. People saw the flash, and many of them did the entirely natural thing, which was to walk to their windows and look. 2.5 minutes later, the shockwave reached the ground and blew the windows in. Around 1,500 people were injured badly enough to seek medical attention. The overwhelming majority of those injuries were lacerations from flying glass. More than 7,000 buildings were damaged. Nobody was killed, which was largely a function of the shallow entry angle and the altitude of the burst. And here is the fact that matters more than any of the others. Nobody saw it coming, not by a day, not by an hour. There was no warning of any kind from any observatory, anywhere on Earth. The first indication humanity had that a 13,000-ton object was arriving was the light in the sky. The reason is almost absurdly simple. The object approached from the direction of the sun. Ground-based telescopes cannot look at the sun. That whole region of the sky is permanently unavailable to us during daylight, and an object coming out of it is invisible until it is in the atmosphere. That is the 5th of the 7, and it is the one where the emptiness we established at the beginning stops being reassuring. Let me repeat the earlier claim, because it is true, and I do not want to walk it back. If you were placed at a random point in the main asteroid belt, the nearest object would typically be around 600,000 miles away. Space is overwhelmingly empty. Collisions are rare. Now hold that word rare up to the light and ask what it means over 4.6 billion years. The best place to check is the moon, and you can start this one yourself tonight. Look at it. Every grey circle you can see with the naked eye is an impact scar, and the moon keeps them because it has no way to erase anything. It has no atmosphere to burn up incoming objects, no weather to erode the results, no plate tectonics to recycle its surface, and no life to build over the evidence. A crater on the moon stays a crater essentially forever. The lunar near side alone carries roughly 300,000 craters wider than half a mile. Across the whole moon there are somewhere on the order of 500,000 craters, over half a mile across. And if you count every impact scar down to the size of a dinner plate, the number runs into the many billions. The surface is not marked. The surface is entirely made of overlapping impacts, one on top of another, all the way down to a layer of pulverized dust several yards thick called the regolith, which is itself just the accumulated wreckage of everything that ever hit. That is what the same 4.6 billion years looks like when nothing erases it. And Earth, which is larger and has stronger gravity, was hit more often than the moon was, not less. We have simply been resurfaced. Rain, wind, oceans, moving continents and growing things have wiped the record almost clean. We know of about 200 confirmed impact structures on the entire planet. That number is not a measure of how often we have been hit, it is a measure of how good Earth is at healing, except for the ones that were too recent to have been covered over yet. On the morning of June 30th, 1908, something exploded in the sky above the Podkamenaya Tunguska River in a remote part of Siberia. The object is estimated to have been somewhere between 160 and 200 feet across, and it never reached the ground. It disintegrated at an altitude of around 5 miles, releasing energy usually estimated in the range of 10 to 15 megatons, though published figures span a much wider range because the constraints are indirect. The shockwave flattened roughly 830 square miles of forest. Around 80 million trees were knocked down, and the pattern in which they fell radiates outward from a central point in a way that is still clearly visible in aerial photographs taken decades later. At the center of the blast area, the trees remained standing but were completely stripped of branches and bark because the pressure wave arrived from directly above. Eyewitnesses at a trading post about 40 miles away described being knocked off their feet and feeling heat intense enough that they thought their shirts were burning. Seismographs registered the event in Britain. For several nights afterward, the sky over northern Europe was bright enough at midnight that people reported being able to read outdoors. And then, remarkably, almost nothing happened for 19 years. Russia was heading into a revolution and a civil war, and a flattened forest in an almost uninhabited part of Siberia was not a priority. The first scientific expedition to reach the site was led by Leonid Kulik in 1927. Kulik expected to find a crater with meteorite fragments in it. He found no crater at all, which confused him for the rest of his career, and which we now understand is exactly what an airburst leaves behind. Here is why Tunguska is the one that should hold your attention rather than Chicxulub. Chicxulub was a 66 million year event. Tunguska was a 100-year event, roughly, based on the best current estimates of how often objects that size arrive. And it landed in one of the emptiest places on the surface of the planet. Shift the timing by about 4 hours, and the same object arrives over St. Petersburg, or over any of the cities along the same latitude band, and the 20th century has a different opening chapter. There were no casualties recorded, though there were almost certainly a small number among the local Evenki people whose reindeer herds were destroyed. The reason the number is essentially 0 is not that the event was small. The event was equivalent to roughly 1,000 Hiroshima bombs. The reason is that Earth's surface is mostly ocean, ice, desert and forest, and cities are a very small target. That is the actual protection. Not our detection network, which did not exist. Not the atmosphere, which broke the object up but delivered the energy anyway. Geography and luck. And you can check that arithmetic against your own life. Earth rotates once every 24 hours, so any incoming object arrives over whatever happens to be underneath it at that moment. Roughly 71% of the surface is ocean. Most of the rest is ice, desert, mountain, forest and farmland. The odds that the ground beneath a given arrival is a city are small. And the reason you have never lived through one of these is that the target you occupy is very, very small. Which brings us to the one that did not heal. In 1980, a geologist named Walter Alvarez and his father Luis, a physicist who had won a Nobel Prize, published a paper about a thin layer of clay. Walter had been working in Italy, at a gorge near the town of Gubbio, on a boundary in the rock that marks the end of the Cretaceous period. Below the boundary, the limestone is full of tiny fossils. Above it, they are largely gone. Between the two sits a layer of clay about 1 centimeter thick. Walter wanted to know how long that layer had taken to form. Luis suggested a method. Iridium is rare in Earth's crust, but relatively common in meteoritic material, and it falls onto Earth at a slow, roughly steady rate as cosmic dust. Measure the iridium in the clay, compare it to the background rate, and you get a clock. The measurement came back roughly 30 times higher than expected. They checked other sites. Denmark, New Zealand. The anomaly was everywhere, in the same layer, worldwide. That is not a clock reading. That is a single event depositing meteoritic material across the entire surface of the planet at once. The paper proposed an asteroid impact as the cause of the mass extinction, and it was received with substantial skepticism. The obvious objection was that there was no crater. It took another decade to find it, buried under half a mile of sediment beneath the Yucatan Peninsula and the Gulf of Mexico, identified partly from old oil exploration survey data that had been sitting in a filing cabinet since the 1950s. The Chicxulub crater is about 110 miles across. The object that made it is estimated at somewhere between 6 and 9 miles wide, arriving at roughly 45,000 miles per hour. The energy released was on the order of 100 million megatons, which is to say several billion times the Hiroshima bomb, delivered in a fraction of a second. But the impact itself did not do most of the killing. This is the part that is worth understanding properly, because it changes what the threat actually is. The impact excavated an enormous quantity of rock and threw it out of the atmosphere on ballistic trajectories. All of that material came back down, all over the world, within hours. Each falling fragment heated the air as it re-entered. Multiply that by the volume of a mountain range and the entire sky, globally, became a source of thermal radiation intense enough to ignite fires. Then came the longer problem. The rock at the impact site happened to be rich in sulfur-bearing minerals. The impact vaporized them and injected sulfate aerosols into the stratosphere, along with an enormous quantity of fine dust and soot from the fires. Sunlight reaching the surface dropped dramatically, possibly for years. Photosynthesis largely stopped. Ocean plankton collapsed, and the food chains built on them collapsed after. Roughly 75% of all species on Earth did not survive. And here is the part that ought to land personally, because it is the reason you can hear this at all. Among the things that made it through were a group of small, unremarkable, burrowing animals that could shelter underground, stay warm without sunlight, and eat almost anything. They had been living in the margins for over 100 million years while the large animals owned the surface. When the surface stopped working, being small and hidden and undemanding stopped being a disadvantage. You are descended from those animals. Every mammal alive is. The reason there is anybody on this planet capable of pointing a telescope at the sky and asking what else is out there is that one object arrived at one angle 66 million years ago and cleared the board. The honest framing is this: it was not the explosion, it was the dust. An impact is a climate event that begins with a bang. Now consider that the same population of objects that produced Chicxulub is still out there, still moving, and still crossing our orbit. So what are we actually doing about it? More than most people assume, and less than would let anyone relax. In 1998, following congressional direction, NASA set what became known as the Space Guard goal. Find 90% of near-Earth objects, larger than about 3,300 feet across, the size range capable of causing global consequences, within 10 years. That target was met a few years late, and today we believe we have found somewhere around 95% of that population. There are estimated to be roughly 850 to 900 of them. None of the known ones are on a collision course with Earth for at least the next century. That is a genuine achievement, and it deserves to be stated plainly. For the largest objects, the ones capable of ending civilization, the search is close to complete, and the answer is currently reassuring. Then Congress raised the bar. In 2005, a new target was set. Find 90% of near-Earth objects larger than about 460 feet across. We are not close. Current estimates put the completion of that survey somewhere in the region of 40 to 45%. There are thought to be around 25,000 objects in that size range, and we have found roughly 11,000 of them. Which means that as you listen to this, somewhere over half of the objects capable of erasing the city you live in are unaccounted for, not hidden, not approaching, simply not yet found. An object 460 feet across is not a species-ending event. It is a regional one. Depending on where it landed, it is a destroyed metropolitan area or an ocean impact with coastal consequences across an entire hemisphere. And we currently do not know where more than half of them are. The evidence that this gap is real arrives regularly. On July 25, 2019, an asteroid designated 2019 OK passed within about 45,000 miles of Earth. That is roughly a fifth of the distance to the Moon, comfortably inside the orbits of some of our satellites. It was around 330 feet across, large enough to devastate a city on impact. It was detected less than 24 hours before closest approach. Astronomers at the time described it in unusually blunt language for the field. One called it a city killer. Another noted that it had come out of nowhere as far as the survey network was concerned, which was accurate, because 2019 OK spent most of its orbit further out and only became bright enough to detect on its final approach. And there is the sunward blind spot, which Chelyabinsk demonstrated and which we still have not closed. Any object approaching from the direction of the sun is effectively invisible to ground-based telescopes. The solution is to put a telescope somewhere other than the ground, looking in infrared, positioned so it can see the region we cannot. That mission exists. It is called NEO-Surveyor. It is designed to work in infrared from a position near the Sun and Earth Lagrange point 1, and it is intended to find objects that are dark and warm rather than bright and reflective. It has not launched yet. The Vera Rubin Observatory in Chile is the other major change. It carries the largest digital camera ever built for astronomy, and it is designed to survey the entire visible southern sky every few nights, continuously, for 10 years. Its expected contribution to the near-Earth object catalogue is substantial, possibly enough on its own to close much of the 460-foot gap. And there is one more thing worth knowing, because it is the only piece of good news in this entire layer that involves us doing something rather than looking. On September 26, 2022, a spacecraft roughly the size of a vending machine, weighing about 1,300 pounds, deliberately crashed into a small moon called Dimorphos at about 14,000 miles per hour. Dimorphos orbits a larger asteroid called Didymos, and the pair was chosen precisely because that orbit could be measured from Earth with high precision. Before the impact, Dimorphos completed an orbit every 11 hours and 55 minutes. The mission was considered a success if that period changed by 73 seconds. It changed by 32 minutes. The reason it works so much better than the minimum threshold is it's self-interesting. The spacecraft's own momentum accounted for only part of the effect. The rest came from the plume of material blasted off the asteroid's surface by the impact, which acted like a rocket exhaust pushing in the opposite direction. Dimorphos turned out to be a loosely bound pile of rubble rather than a solid body, and rubble throws off far more material than solid rock does. So the honest bottom line on this layer is genuinely mixed, and I think the mixture is more interesting than either extreme. We have found nearly all the largest objects, and none of them are coming. We have found less than half of the city-sized threats. We cannot see anything approaching out of the sun. We have demonstrated once that we can move an asteroid, provided we find it years in advance. And the entire global budget for planetary defense is a small fraction of what a single regional impact would cost. You are alive during the first century in 4.6 billion years in which the planet can see some of it coming and occasionally do something about it. Every previous generation was defenseless and did not know it. That is new. It is also incomplete. 2 more numbers before we leave this layer, because they connect back to the beginning. On April 13th, 2029, an asteroid called Apophis, roughly 1,100 feet across, will pass within about 20,000 miles of Earth. That is closer than our geostationary satellites. It will be visible to the naked eye from Europe and Africa as a point of light moving visibly against the stars. It will not hit us. We have tracked it well enough to rule that out for the foreseeable future. And in July of 1994, the comet Shoemaker-Levy 9, which had been torn into a string of fragments by Jupiter's gravity on a previous pass, struck the planet over the course of 6 days. The largest impact scars were larger than Earth and remained visible for months. It was the first time humanity ever watched 2 solar system bodies collide. 15 years later, in July of 2009, an amateur astronomer in Australia named Anthony Wesley, observing from his backyard, noticed a dark spot on Jupiter that had not been there before. He alerted the professionals. It was a fresh impact scar from an object nobody had detected in advance. Jupiter takes hits regularly. It is large, it is massive, and it sits in a position where it intercepts a meaningful amount of incoming material, which is the last thing to say about this layer, and it is the honest complication. Jupiter is often described as our shield. The reality is more ambiguous. Jupiter does intercept some objects and eject others from the solar system entirely, but its gravity also perturbs distant bodies onto new orbits and sends some of them inward. Modeling work over the last 2 decades has gone back and forth on whether a planet like Jupiter is net protective or net dangerous for a world like ours, and the current answer is that it depends heavily on the specific population you're asking about. The largest object in the solar system after the Sun is doing something to the traffic. We are not fully certain in which direction. That is the 5th of the 7, and it is the last one that involves anything physically hitting us. Now we get to the one that took the longest to find, because it could not be discovered without computers, and it is the one that quietly removes the floor from underneath everything you have assumed so far. In 1889, King Oscar II of Sweden offered a prize for the answer to a question that had been bothering mathematicians for 2 centuries. Is the solar system stable? It was a reasonable question to expect an answer to. Newton had published his laws of motion and gravitation 200 years earlier, and they worked extraordinarily well. Given the position and velocity of 2 bodies, you could calculate their positions at any point in the future exactly. In closed form, with a pencil, Halley had used the method to predict the return of a comet. Leverrier had used it to predict the existence and location of Neptune before anyone had seen it, and it had been found within a degree of where he said it would be. The confidence this produced is difficult to overstate. Pierre-Simon Laplace had written that an intellect which knew the position and velocity of every particle in the universe could calculate the entire future with certainty. The universe was a mechanism. You wound it up and it ran. The prize was awarded to Henri Poincaré. And then, while his winning paper was being prepared for publication, Poincaré found an error in it. He had assumed a certain series would converge. It did not. He wrote to the editor and had the printed copies recalled at his own expense, which cost him more than the prize money. What he found in the corrected version is the reason we are still talking about it. 2 bodies orbiting each other can be solved exactly. Add a third, and the system generally cannot be solved in closed form at all. Worse, Poincaré showed that the trajectories in such a system can be so sensitive to their starting conditions that arbitrarily small differences in where you begin lead to completely different outcomes later. Not slightly different, unrecognizably different. He had discovered deterministic chaos 70 years before the word would be attached to it, while trying to prove the solar system was a clock. This is the 6th of the 7, and it is the one I find genuinely difficult to hold in my head, because it contradicts the single deepest assumption most people have about the sky, the assumption that the orbits are permanent. Let me build the intuition first, because the mathematics is not the point, and the intuition is. Take an ordinary pendulum, a weight on a string, pull it back and let go, and it swings in a completely predictable arc. Release it from a slightly different starting position, and you get a slightly different arc. Small change in, small change out. You can predict where it will be an hour from now, or a year. Now attach a second pendulum to the bottom of the first, so the arm has a joint in the middle. The behavior changes completely. A double pendulum swings, flips, stalls, and reverses in patterns that never repeat. And if you release it twice from starting positions that differ by an amount too small to measure, the 2 motions will track each other for a few seconds, then diverge, and within a minute they are doing entirely unrelated things. Nothing random has been introduced. The physics is exactly the same, exactly deterministic, exactly Newtonian. What changed is that tiny uncertainties now grow instead of staying small. That is the solar system, not a pendulum, a double pendulum with 8 arms. Every planet pulls on every other planet, continuously, forever. The pulls are small compared to the sun's grip, which is why the orbits look clean over human timescales. But small does not mean zero, and the pulls never stop, and over long enough spans they accumulate in ways that cannot be predicted by any method we have or are likely to have. The number that quantifies this has a name. The Lyapunov time is the interval over which a small uncertainty grows by a factor of about e, roughly 2.7. For the inner solar system, the measured value is approximately 5 million years. That is the abstract version. Here is the concrete one, and it is the sentence that reorganized how I think about this subject. Suppose you knew the position of every planet in the solar system today to within 1 foot, a measurement of impossible, absurd precision, far beyond anything we can actually achieve. Feed those positions into a perfect computer with no rounding errors and let it run forward. The predictions would be excellent for tens of millions of years. Then the uncertainty, growing by roughly a factor of 10 every 10 million years, would start to matter. Within about 100 to 150 million years, that original 1 foot uncertainty would have expanded until you could no longer say where Earth is in its orbit, not whether Earth still exists, not roughly how far it is from the Sun, simply where along the ellipse it happens to be at that moment. The answer becomes somewhere on the orbit, and there is nothing you can do about it. Measuring more precisely does not help in any meaningful way, because the growth is exponential. Improving your initial measurement by a factor of 1 million buys you about another 60 million years of validity, and then you are in the same position. The solar system is deterministic and unpredictable at the same time. Those two things are not in conflict. That is the part that takes a while to sit with. So what does this actually mean for the planets? Does it mean anything, or is it a mathematical curiosity? For a long time, nobody knew, because you cannot answer that question with pencil and paper. You need to integrate the equations of motion for the entire system forward across billions of years, and that requires an enormous quantity of arithmetic performed with extreme care about accumulating numerical error. Jacques Lascar, at the Paris Observatory, has spent most of his career on exactly this problem. In 1989, he published the first long integration showing the chaotic behavior of the inner planets. And in 2009, with Michael Gastineau, he published the result that everyone now cites. They ran 2,501 separate simulations of the solar system forward for 5 billion years. In each one, they varied Mercury's starting position by tiny amounts, on the order of a few feet, to sample the range of possibilities consistent with what we actually know. In about 99% of the runs, nothing dramatic happened. The planets stayed roughly where they are. Orbits wobbled, eccentricities drifted, but the architecture held. In about 1% of them, it did not. Mercury is the vulnerable one. It is the smallest planet, it is closest to the Sun, and its orbit is already the most eccentric of the 8. In the unstable runs, a resonance develops between Mercury's orbit and Jupiter's, and Mercury's eccentricity begins to climb. Once it climbs far enough, the orbit crosses Venus's. From there, the outcomes vary. In some runs, Mercury is ejected from the solar system entirely. In some, it falls into the Sun. In some, it collides with Venus. And in a small number of the runs, the disruption propagates inward and outward. Lascar and Gastineau ran a set of detailed follow-up simulations from one of the destabilized cases and found scenarios ending in a collision between Mars and Earth, and scenarios ending in a collision between Venus and Earth. Now, the honest framing, because this is exactly the kind of finding that gets stripped of its context. 1% over 5 billion years is a small probability across an enormous span of time. It is not a forecast, it is not a prediction that anything will happen. The Sun will have become a red giant and rendered the question academic long before most of those scenarios play out. And the result depends on modelling choices that different research groups implement differently, though the broad finding of inner system chaos is now well established and has been reproduced independently. But notice what the result actually overturns. Not the safety of Earth in any practical sense. What it overturns is the idea that the arrangement is fixed. The planets are not sitting in permanent slots. They are in a configuration that has been stable so far, that is very likely to remain stable, and that has a small but genuinely non-zero probability of rearranging itself. The clockwork is not a clock, it is a system that has been behaving like a clock for as long as anyone has been watching. And you should understand that nobody has been watching for very long. And this is not merely theoretical, because we can see the mechanism operating in the present, in a place where it has already finished its work. Go back to the asteroid belt. If you plot the number of asteroids against their distance from the Sun, the distribution is not smooth. There are sharp gaps in it, discovered by Daniel Kirkwood in 1866, at very specific distances. Each gap sits at a location where an asteroid's orbital period would be a simple fraction of Jupiter's. The largest is the 3-to-1 gap, where an object would orbit exactly 3 times for every 1 Jupiter orbit. Here is why that empties out. Think about pushing a child on a swing. If your pushes arrive at random moments, they mostly cancel out and nothing much happens. If they arrive in time with the swing, every push adds to the last one, and the amplitude grows. That is resonance, and it works the same way in orbital mechanics. An asteroid in a 3-to-1 resonance with Jupiter receives its gravitational tug from Jupiter at the same point in its orbit over and over for millions of years. The tugs reinforce, the orbit stretches. Eventually it stretches far enough to cross the path of Mars or Earth, and the object is either flung out of the solar system, dropped into the Sun, or hits something. The Kirkwood gaps are not places where asteroids never formed. They are places that have been cleared out, one object at a time, over billions of years by a rhythm. And here is the complication that stops this from being a simple story about resonance as a destroyer. Pluto's orbit crosses Neptune's. That is a genuinely strange fact once you notice it. For about 20 years out of every 248, Pluto is closer to the Sun than Neptune is. Most recently that happened between 1979 and 1999, during which time the outermost planet in the solar system was Neptune, not Pluto. 2 objects on crossing orbits should eventually meet. Over 4.6 billion years, it should already have happened many times over. It cannot happen, and the reason is a resonance. Pluto completes exactly 2 orbits for every 3 that Neptune completes. That precise ratio means the 2 bodies never arrive at the crossing point together. The geometry repeats, locked, and every time Pluto approaches the region where Neptune's orbit lies, Neptune is reliably somewhere else. The resonance is not a coincidence that happens to hold. It is actively self-correcting. Nudge Pluto slightly out of the rhythm and the gravitational interaction pushes it back in. So the same mechanism that empties the Kirkwood gaps also protects Pluto permanently from the one object that could destroy it, and it is not alone. There are more than 400 known objects in the same 2 to 3 resonance with Neptune, collectively called Plutinos, all of them held in the same protective rhythm. That is worth stating carefully, because it is the most balanced thing I can say about this entire layer. Chaos is not the same as destruction. The solar system is not falling apart. What it is doing is far more interesting than that. It is continuously sorting itself, over billions of years, eliminating the configurations that cannot persist and locking in the ones that can. What survives is not what was designed. It is what happened to be stable. We are looking at the survivors, and a meaningful fraction of the objects that have arrived at Earth got here through exactly that door. The 3-to-1 gap and a neighboring resonance are among the primary delivery routes that move material from the main belt into the inner solar system. The 5th layer and the 6th layer are the same layer, viewed at different timescales. Now the part that is closest to home. Chaos does not only affect where a planet is, it affects how a planet is oriented. Earth is tilted about 23.4 degrees relative to its orbital plane. That tilt is the entire reason seasons exist. It varies, slowly, between roughly 22.1 and 24.5 degrees over a cycle of about 41,000 years. Our orbital eccentricity varies on cycles of roughly 100,000 and 405,000 years. The direction the axis points precesses over about 26,000 years. Those variations are called the Milankovitch cycles, after the Serbian engineer Milutin Milankovic, who worked out the mathematics in the 1920s and 30s, much of it while interned during the First World War. They change how sunlight is distributed across latitudes and seasons, and they are the primary pacemaker of the ice ages. The evidence for this is written into ocean sediment cores and ice cores, where the isotope records show the same periodicities. So the wobble is not hypothetical. It has been driving the climate of this planet for millions of years, and the fact that you live in an interglacial period rather than under a mile of ice is downstream of orbital geometry. Sit with that for a moment, because it is easy to read past. Whether the place you live is a city or a glacier is not decided locally. It is decided by the shape of this planet's orbit and the angle of its axis, both of which are set by the gravitational pull of planets hundreds of millions of miles away, on cycles tens of thousands of years long. 20,000 years ago, ice more than half a mile thick sat on top of what is now Chicago, Manchester, and Stockholm. Nothing about those places changed. The geometry changed. Now look at Mars. Mars has no large moon. Its axial tilt is currently about 25 degrees, close to ours. But simulations, many of them again by Laskar and colleagues, show that Martian obliquity is chaotic, and that over the last few tens of millions of years it has likely varied between roughly 10 and 60 degrees. At 60 degrees, the poles receive more annual sunlight than the equator. The polar ice caps sublimate, the atmosphere thickens, and ice is deposited at the equator instead. Mars has done this repeatedly. We can see the evidence in layered deposits at the poles and in glacial features found at mid-latitudes where no ice should currently be. Then Laskar and his collaborators asked the obvious follow-up question: what would Earth's obliquity do without the Moon? The answer, published in 1993, was that Earth's tilt would be chaotic too, varying across a range of roughly 0 to 85 degrees over timescales of millions of years. 85 degrees means the planet is lying on its side. The pole faces the sun directly for half the year and points into darkness for the other half. There is no meaningful equator and no stable climate zone anywhere on the surface. Wherever you happen to live on that version of Earth, you would spend half the year in permanent daylight and half in permanent dark, and so would everybody else. The seasonal swing at every latitude becomes extreme beyond anything in our geological record. The Moon prevents this. It is massive enough and close enough that the torque it exerts on Earth's equatorial bulge dominates the perturbations from the other planets, and it locks our tilt into a narrow range. And the Moon exists because of an impact. The standard model is that a body roughly the size of Mars, usually called Theia, struck the young Earth about 4.5 billion years ago, and the Moon condensed out of the debris, which produces a conclusion I want to state carefully, because it is easy to overreach here. The stability of Earth's seasons, over the geological timescales on which complex life evolved, appears to depend on a collision, not on a law, on an event. There is one more piece to this layer, and it is the largest one. The planets did not form where they are. Multiple lines of evidence, developed principally over the last 25 years, indicate that the giant planets moved substantially after they formed. The most influential version of this is the Nice model, named for the French city where the collaborating researchers were based, published as a set of papers in 2005. In the model, the giant planets form in a more compact arrangement than we see today, surrounded by a disk of leftover icy debris. Interactions with that disk cause the planets to slowly migrate. Jupiter drifts slightly inward. Saturn, Uranus, and Neptune drift outward. Eventually, Jupiter and Saturn cross a resonance, and the resulting kick destabilizes the outer system, scattering Uranus and Neptune outward through the debris disk and flinging an enormous quantity of icy material in every direction, including inward. In some versions of the model, Uranus and Neptune swap places. The model was originally constructed in part to explain a specific observation. The lunar samples returned by Apollo suggested a spike in impacts around 3.9 billion years ago, several hundred million years after the Moon formed, which came to be called the Late Heavy Bombardment. The timing of that spike, and whether it was a genuine spike or an artifact of where the Apollo missions happened to land, is now actively debated. But the broader picture of substantial giant planet migration is supported by independent evidence, including the structure of the Kuiper Belt and the distribution of Jupiter's Trojan asteroids. There is a more aggressive proposal as well, called the Grand Tack, in which Jupiter migrates inward to roughly the current orbit of Mars before Saturn catches it in a resonance, and both planets reverse course and move back out. If something like that happened, it would explain why Mars is so small, by depriving it of material during formation, and it would have thoroughly scrambled the inner solar system in the process. These models are not settled, they are actively contested, and they are revised regularly. I am telling you about them not because we know they are right, but because of what even the disagreement establishes. The arrangement in front of us is not the original one. The planets moved. The current spacing is the outcome of a violent reorganization, not a design, and the calm we measure today is what a system looks like after the unstable configurations have already been eliminated, one collision and one ejection at a time. That is the sixth of the seven, and it is the deepest one. Every previous item was about something in the solar system being dangerous. This one is about the solar system's own structure being provisional, which leaves exactly one question. If the arrangement is not permanent and the calm is a phase, then how long does the phase last? We can actually answer that. And the answer does not depend on the 1% chance of anything unusual happening. It happens on schedule. It is already underway, and the mechanism is the same one that killed Venus. In 1972, Carl Sagan and a graduate student named George Mullen published a short paper about a problem that should not have existed. Stellar physics is one of the better understood areas of astronomy. We know how stars of a given mass evolve, and the models are constrained by observations of millions of them at every stage of life. Those models say something unambiguous about our own star. The Sun was fainter in the past, substantially fainter, about 70% as bright when it formed, brightening steadily ever since as its core grows denser and hotter. Sagan and Mullen ran the obvious calculation. Take a young sun putting out 70% of today's energy, apply it to a young Earth, and work out the surface temperature. The answer was that Earth's oceans should have been frozen solid for roughly the first 2 billion years of the planet's existence. The geological record says otherwise, and it says so emphatically. There are sedimentary rocks in Greenland dating back nearly 3.8 billion years, and sediment requires flowing water to deposit it. There are zircon crystals from Western Australia, over 4.4 billion years old, whose oxygen isotope ratios indicate they formed in the presence of liquid water within about 150 million years of Earth's formation. The Sun was too dim for liquid water. Liquid water was there anyway. That is the faint young sun paradox, and it has generated 50 years of work, and the resolution is probably some combination of a much thicker greenhouse atmosphere in the early Earth, less land area, and therefore lower reflectivity, and possibly fewer clouds. The details remain genuinely open, but the part relevant to tonight is not the paradox. It is the premise underneath it, which nobody disputes. The sun is getting brighter. It is doing it right now, and it does not stop. This is the seventh and last of them, and it is different from the other 6 in one important way. Everything else tonight has been a risk, a probability, something that might happen, or that happens rarely, or that happened once. This one is not a risk. It is a schedule. The rate is roughly 1% brighter every 110 million years. That is imperceptibly slow on any human timescale, and it is overwhelming on a geological one. To see what it does, you need to understand the thermostat it is working against, because Earth has one, and it is remarkable, and it is going to lose. The thermostat is the carbonate-silicate cycle. Carbon dioxide in the atmosphere dissolves into rainwater, forming a weak acid. That rain falls on silicate rock and chemically weathers it, and the dissolved products are carried by rivers to the ocean, where they are eventually locked into carbonate rocks on the sea floor. Plate tectonics carries those rocks down into the mantle, and volcanoes return the carbon to the atmosphere over hundreds of millions of years. The feedback is the elegant part. Warmer temperatures mean more rainfall and faster chemical weathering, which pulls carbon dioxide out of the air faster, which cools the planet. Colder temperatures slow the weathering down. Volcanic carbon dioxide accumulates, and the planet warms back up. This system has kept Earth's surface temperature within the range that permits liquid water for something close to 4 billion years, through an increase in solar output of more than 30%. That is a genuinely extraordinary piece of self-regulation, and it is the main reason you are here. And notice what it is made of: rain, rock, rivers, and moving continents. The thermostat holding this planet in the habitable range is not a delicate mechanism. It is the weather and the geology you live on top of, running as one connected system on a timescale of hundreds of millions of years. You are standing on the machine. Now watch what happens as the sun keeps brightening. To hold the temperature steady against increasing sunlight, the thermostat has to keep reducing atmospheric carbon dioxide concentration reaches a floor. Because plants need carbon dioxide to concentration reaches a floor. Because plants need carbon dioxide to photosynthesize. Most plants use a photosynthetic pathway called C3, and it stops functioning at concentrations somewhere around 150 parts per million. A smaller group, including many grasses and important crops like maize and sugarcane, use a pathway called C4 that can operate down to around 10 parts per million. Current estimates put the C3 threshold somewhere in the range of 500 million to 900 million years from now, with C4 plants persisting for a while after that. The error bars on these numbers are wide, and different modeling assumptions move them around by hundreds of millions of years. But the direction is not in question. When photosynthesis fails, the base of the food chain goes with it, and then atmospheric oxygen begins to decline, because free oxygen in our atmosphere is continuously produced by life and would otherwise be consumed by oxidation within a few million years. Some recent modeling work suggests Earth's oxygen-rich atmosphere may have a remaining lifespan on the order of 1 billion years, and that the transition, when it comes, could be relatively rapid in geological terms. So the first thing to go is not the water, it is the plants, then the water goes. As solar output continues to rise, the surface warms past the point where the thermostat can compensate, and evaporation increases. Water vapor is a greenhouse gas, so more vapor means more warming, which means more evaporation. That is the same loop Venus ran, and it is called the moist greenhouse. Once enough water vapor reaches the stratosphere, ultraviolet light breaks the molecules apart, and the hydrogen escapes to space. Every hydrogen atom that leaves is a molecule of water that will never reform. The oceans do not boil away dramatically. They leak, molecule by molecule, upward and out. Current estimates put the onset of that process somewhere between 1 and 1.5 billion years from now, with complete loss of the oceans following over the subsequent billion years or so. By roughly 2 to 3 billion years from now, Earth is expected to be a dry, hot world with a thick carbon dioxide atmosphere and a surface temperature that would melt several metals. Which is to say, Earth becomes Venus, not by analogy, by the same mechanism, running the same way, arriving a few billion years later because we started further out. And only then, long after all of that has finished, does the part everybody has heard of actually happen. In roughly 5 billion years, the Sun exhausts the hydrogen in its core. The core contracts and heats. Hydrogen fusion moves into a shell around it, and the outer layers expand enormously. The Sun becomes a red giant, swelling to somewhere on the order of 200 times its current radius, while its surface cools to a deep orange. Mercury and Venus are certainly engulfed. Earth's fate is less certain, and the uncertainty is interesting. As the Sun expands, it also loses a substantial fraction of its mass in a slow, dense wind, and as the Sun loses mass, its gravitational grip weakens and the planets spiral outward. So there is a race between the expanding surface and the retreating orbit. Most current modeling suggests Earth loses that race and is engulfed, but the result is sensitive to the mass loss rate, and it remains genuinely debated. It does not matter much either way. The Earth that is or is not engulfed will have been a sterilized rock for billions of years by then. Afterward, the Sun sheds its outer layers entirely, and what remains of the core settles into a white dwarf, an object about the size of Earth containing over half the Sun's original mass, so dense that a teaspoon of it would weigh several tons. It will not fuse anything. It will simply cool, slowly, for a very long time. Now let me pull the timing together, because the arithmetic here is the point of the entire layer. Life has existed on Earth for at least 3.5 billion years, and probably closer to 4. For the overwhelming majority of that span, it was microbial, complex multicellular life, the kind that leaves fossils you can see without a microscope, has been around for roughly 600 million years. Animals on land, roughly 400 million. Our own genus, about 2 to 3 million. Written history, about 5,000. And the remaining window for complex life on the surface of this planet, before the carbon dioxide floor and then the moist greenhouse close it, is somewhere in the range of 500 million to 1 billion years. Put those two numbers next to each other. Complex life has had about 600 million years. It has somewhere between 500 million and 1 billion left. We are not near the beginning. We are somewhere around the middle, possibly past it. I want to put that in a form you can actually feel, because 1 billion years is another one of those numbers the brain files away and stops thinking about. Compress the whole window for complex life, start to finish, into a single day. Animals appear a little after 9 in the morning. The dinosaurs arrive around lunchtime and are gone by early evening. Our own species shows up in the last 4 seconds before midnight, and everything anyone has ever written down happens in the final 10th of a second. And it is not midnight. On that clock, it is somewhere around 2 or 3 in the afternoon. There is a great deal of day left. There is also, for the first time in the history of this planet, something on it that knows what time it is. The era of visible, complicated, interesting life on Earth is not a permanent condition that started once and continues indefinitely. It is a window, it has a width, and you are living a long way inside it rather than near the front. I want to be honest about the confidence here, because the error bars are large, and I would rather you have the uncertainty than a false precision. The estimates for the carbon dioxide floor depend on assumptions about continental growth and weathering rates that are difficult to constrain. The moist greenhouse threshold depends on cloud behavior in a hotter atmosphere, and clouds are the single largest source of uncertainty in climate modeling at any timescale. Different papers give answers that differ by a factor of 2, but no model gives an answer of forever. The direction is fixed by stellar physics, which is the part we understand best of all. And there is a second clock running underneath the first one, which gets far less attention. Earth's magnetic field, the thing we established in the third layer, is one of only 2 things standing between you and the radiation environment outside. Is generated by convection in the liquid outer core. That convection is driven by heat escaping from the interior, some of it left over from formation, and some of it from the decay of radioactive elements. Both sources are finite. The planet is cooling. As it cools, the solid inner core grows, and the liquid layer that generates the field thins. Mars is the demonstration. Mars is about half Earth's diameter, which means it has a much higher surface area relative to its volume, which means it lost its internal heat far faster. Its dynamo shut down within the first several 100 million years. The magnetic field went with it, the solar wind stripped the atmosphere, and the surface water was gone. Earth is larger and cooling more slowly, and estimates for how long our dynamo can persist generally run to a few billion years, well beyond the point at which the surface becomes uninhabitable for other reasons. So this is not the clock that matters for us. But it is worth knowing it exists, because it makes the same point in a different register. Every protective feature of this planet is a process, not a property. The magnetic field is a running engine. The atmosphere is a balance between what escapes and what is replenished. The temperature is a thermostat with a limited operating range. The tilt that gives you seasons is held steady by a moon that is currently backing away from you at about 1.5 inches per year. None of them are permanent because none of them are things. They are all activities, and activities run down. Take the moon, since we have already established how much depends on it. The moon is receding from Earth at about 1.5 inches per year. We know this with extraordinary precision because Apollo 11, 14, and 15 left retroreflector arrays on the surface, and observatories have been bouncing laser pulses off them continuously since 1969. The round trip takes about 2.5 seconds, and the timing is accurate enough to measure the distance to within a few millimeters. The cause is tidal friction. Earth's rotation drags its tidal bulge slightly ahead of the moon, and the gravitational pull of that displaced bulge accelerates the moon forward, which raises its orbit. The energy comes out of Earth's rotation, which is why our days are getting longer. Growth bands in fossil coral from the Devonian period, around 400 million years ago, record roughly 400 days in a year, which means a day back then was about 22 hours long. 1.5 inches a year is nothing. Over 400 million years it is about 6,000 miles. The moon will not escape. The sun will end this story long before that becomes a question. But the stabilizing torque it provides weakens as it moves away, and the arrangement that holds Earth's tilt in a narrow band is, like everything else tonight, a condition rather than a fact. And on a longer clock still, the galaxy itself is not leaving us alone. The Andromeda Galaxy is approaching the Milky Way at about 250,000 miles per hour, and current estimates put a first close encounter somewhere in the region of 4 to 5 billion years from now, though recent work using improved measurements of Andromeda's sideways motion has raised real uncertainty about whether a direct merger is guaranteed at all. If it happens, almost nothing collides. The stars in a galaxy are so far apart relative to their size that a merger is mostly two clouds passing through each other, rearranging orbits without a single stellar impact. What it would likely do to our solar system is move it. Simulations suggest a reasonable chance that the Sun ends up flung into a much wider orbit, further out in the merged galaxy than it is now. By then, the Sun is a red giant or a white dwarf, and the question of where it sits is academic. But it is worth noting, at the end of a list of things the diagram left out, that the diagram also left out the fact that the whole assembly is moving. The Sun is orbiting the galactic center at about 514,000 miles per hour and takes roughly 230 million years to complete one circuit. It has done that around 20 times since it formed, the last time you were in this part of the galaxy, and you were, because the atoms in your body were already here. Dinosaurs had not yet appeared. That is the seventh of the seven, and it is the last one. So where does that leave us? Let's pull all seven together, because they are not a list. They stack, and the shape they make is the actual answer to the question we started with. The first was distance, and distance turned out to be the strangest item on the list, because it is the only one that protects us. It is why almost nothing out there ever reaches us, and it is also why nothing could ever reach us in time if it did. The second was the surfaces, and every one of them is a demonstration of what this planet was one variable away from becoming. Venus is what happens with slightly more sunlight. Mars is what happens with slightly less mass. The third was the radiation, and it is the one that cannot be seen. The fourth was the Sun, which is not a lamp, but a variable magnetic object that has twice in living memory come close to showing us what it does to a wired planet. The fifth was the traffic, hundreds of millions of loose bodies, more than half of the dangerous ones still uncatalogued, arriving on a schedule we can only describe with statistics and a shrug. The sixth was the chaos, the discovery that the orbits are not permanent, cannot be predicted past about 100 million years by anyone, ever, and have demonstrably been rearranged at least once already. And the seventh was the clock, the one that is not a risk at all, because it is already running, on a schedule we can calculate, and it ends the same way Venus ended. Now look at the same 7 layers as a set of clocks, because they operate on wildly different timescales, and that is what makes them so easy to dismiss one at a time. On the scale of minutes, the sun can black out radio across an entire hemisphere before anyone knows it has happened. On the scale of hours, a coronal mass ejection crosses 93 million miles and pushes current into every long conductor we have built. On the scale of a single day, an undetected object arrives out of the direction of the sun and breaks every window in a city. On the scale of a human career, an astronaut in transit accumulates a dose that no shielding we can currently afford to launch will prevent. On the scale of centuries, a Carrington-class storm is not unlikely. It is somewhere between plausible and expected. On the scale of 100,000 years, the tilt of this planet and the shape of its orbit move enough to advance and retreat continental ice sheets. On the scale of 100 million years, an object large enough to collapse the global food chain arrives, and we know this because the last one left a layer of clay you can put your finger on. On the scale of 1 billion years, the thermostat runs out of room, the plants fail, and the oceans begin to leave. And on the scale of 5 billion years, the star at the center of all of it stops being a star. Every one of those clocks is running right now. Not one of them is waiting for anything. So here is the honest bottom line, and it is simple, and it is a little humbling. The solar system is not dangerous because it is hostile. It has no disposition at all. It is gravity, thermodynamics, orbital mechanics, and nuclear physics running without supervision for 4.6 billion years across a volume so large that the word neighborhood is a joke. Every one of the 7 layers is just those same laws, operating at a scale that has no reference to us. What is remarkable is not that the system is violent. Given the physics, the violence is the expected result. What is remarkable is the exception. One rocky planet, at 93 million miles from a stable star, large enough to hold its atmosphere and retain its internal heat, with a magnetic field still running, a moon large enough to hold its tilt steady, plate tectonics keeping a chemical thermostat in operation, and enough water to matter, but not so much that it drowned the whole surface. Every one of those conditions is a coincidence. Several of them are the direct consequences of ancient collisions, and all of them together produced a window, hundreds of millions of years wide, in which something on the surface could become complicated enough to look up and start asking questions about the rest of it. We are inside that window right now, not at the start of it, somewhere in the middle. And within the last century, a species inside that window figured out how to measure the whole thing. We worked out how bright the sun used to be by reading rocks. We found the crater by reading iridium in a centimeter of clay. We discovered the orbits are chaotic by building machines that could do the arithmetic. Poincaré could not. We measured the radiation on the way to Mars by leaving an instrument switched on inside an empty capsule. We moved an asteroid on purpose on the first attempt. None of that changes any of the 7 layers. The distances are still the distances. The sun is still going to do what it does. But the difference between a species that does not know and a species that does is not nothing. It is, as far as we can tell, the only thing in the solar system that has ever been new. So here is what I would leave you with, and it does not require a telescope. Go outside after sunset, on any clear evening, and find the brightest point of light in the sky that is not the moon. Most of the year, that is Venus. You have almost certainly seen it 1,000 times and assumed it was a star. It is not a star, it is the control group. Venus formed at the same time we did, out of the same cloud, around the same sun, at 95% of our size. It got oceans. It may have kept them for 2 or 3 billion years, which is longer than complex life has existed here, and then the thermostat lost. The water went up into the sky and never came back down. And today the surface is 867 degrees under an atmosphere that would crush a submarine. Nothing exotic happened to Venus. No impact, no catastrophe, no bad luck. It simply Saturday 26 million miles closer to the fire than we did and ran the same processes we are running. And that was enough. That point of light is the single most useful object in the sky, because it is the only place we can look and see the alternative outcome. Same experiment, different result. And it is bright enough to see from a city street with no equipment at all. The solar system does not look terrifying, and that is the honest reason all 7 of these went unnoticed for so long. Distance is invisible, radiation is invisible, chaos is invisible across a human lifetime. A star brightening by 1% every 110 million years is invisible across a civilization. The calm is real. It was never the same thing as safety. Thank you for joining me tonight on this trip through the 7 reasons this planet should not have made it, and somehow did. If you found this as fascinating as I did, please take a moment to like this video and subscribe to the channel. It genuinely helps this channel keep making these deep dives into the cosmos. So the next time you catch that bright point in the evening sky, remember what you are actually looking at. Not a star. A world the same age as this one, built from the same material that ran out of room. And then remember that you are standing on the only one of the 4 that is still keeping its water, still holding its air, and still, for now, winning.